Hello, everyone. Thanks for coming to my talk. Thanks to the conveners for inviting me to give an overview about the seismic constraints on the structure of Alaska. This is the collaborative group work born from the 2021 EarthScope Alaska workshop. Inspired by the discussions during the workshop, a group of us came together and started working on a compilation and comparison of seismic structures in Alaska. This is an ongoing work. Stay tuned for more results. I'm here today to report what we have done so far. Accretionary terrains and subduction zone made the key components of Alaska's tectonic history. On top of that, this place in Alaska, it houses a lot of secrets about the tectonic evolution of the Earth. Since 2015, the EarthScope transport array arrived in Alaska. This array has greatly improved the seismic data coverage in Alaska. With the improved data coverage, a lot of seismic models have been published in Alaska, focusing on different stories using different methods. So we have collected a lot of models, including 17 seismic models in Alaska and the Yukon region in Western Canada. We have collected tomographic models and receiver function results as well. Today, I'm not able to show you all the detailed comparisons of all these models. Instead, we focus on understanding about the two major topics we have discussed, including signatures of tectonic terrains from seismic models and the image of 3D subduction geometry. Let's first look at tectonic terrains. Alaska has a lot of tectonic terrains. I'm highlighting a few major terrains in Alaska, including the accretionary terrains in southern Alaska, the Koyukuk terrains in western Alaska, the Arctic Alaska terrains, and the North American terrains in eastern Alaska and the Yukon region in western Canada. Conventionally, once we have a seismic velocity model, we will look at the depth slices to know the velocity distribution. And these are the three depth slices from three velocity models. They provide very valuable information about the velocity distribution in certain regions. However, we want to focus more on the overall pattern of the velocity structure within a certain layers or depth range. To do that, we employed a k-means clustering algorithm to cluster the velocity profiles. We focused on 5 to 50 kilometers depth range during this presentation. The figure here shows the superimposition of all velocity profiles from the model by Burke et al. 2020. After running the k-means clustering, we are able to group seismic velocity profiles into a few clusters. After plotting the location of the clusters on a map, we are able to compare the distribution of velocity clusters with tectonic terrains, showing as the purple lines. So here are three of the clustering results we have done. From these three models, we can see some consistent clustering patterns, including the northern Alaska clusters, southern Alaska clusters. There are also a lot of other features that you can get from this clustering result. But some of you may be familiar with the Moho depth or crustal thickness. So we want to check whether our clustering result is dominated by crustal thickness patterns. To do that, we plotted Moho depth maps from three different models. All of these three models show thickest crust in northern Alaska, covering the Arctic Alaska terrains. The thinnest crust occurs in the interior of Alaska. While the southern Alaska part, we have complicated moho patterns due to the flat subduction of the Xiaotao plate. To further investigate the influence of moho distribution on the clustering result, we plotted the histograms of moho distribution within each cluster, as shown here for example. The x-axis is the cluster number, y-axis is the moho value from Miller et al. 2018 model. In overall, there are differences, but we cannot say they are distinctly different. By getting the range, the most of the moho depths are within 30 to 50 kilometers for this region. We also plotted the centers and compare that with the moho range. While the moho range is between 30 to 50 kilometers, a lot of velocity variations also occur in shallower parts, shallower than 30 kilometers. In summary, we could say that we do see clustering patterns that reveal very interesting groups of velocity structures that are independent of crustal thickness. This could be further reflected by a detailed comparison between the clustering result on the left and the moho depth distribution on the right. Particularly when you're looking at northern Alaska. For moho depths, most of our northern Alaska is characterized by deep moho, while the clustering result shows 2 clusters. And this is interestingly coincident with the continental margin setting of Arctic Alaska and the arc setting of Alaska into a different region. This is continental margin setting, this is the arc setting. And we also see an interesting cluster within the interior of Alaska that is not shown from the moho depth pattern. Like this clustering result with consistent patterns across all models indicate that we do see control of velocity structure from tectonic terrains. The second topic we want to show today is on 3D subduction geometry. In Alaska, there are a lot of complicated subduction related structures. We have the Pacific plate subducting to northwest and the Xiaotao microplate subducting to northwest as well. They both are subducting beneath the North American continent. They are at a curved margin and they have complicated history and structures. We want to check whether we are able to resolve the 3D slab geometry and the gaps between slab segments, and whether we see any slab signature below the Wrangell volcanoes. These are 3 vertical velocity profiles along slab depth contour of 40 kilometers. What we see is the separation of high velocity features, going all the way from the Pacific section to the Xiaotao section. We see a variation or a strong variation of velocities from high velocity, lower velocity, a high velocity again, and lower velocity. Those are consistent with major slab segments we expect and we see from other models. And this Book et al. Model shows a complicated pattern, but we see the variation from high to low and high. This is also shown from Yang and Gao's model. However, we admit the inconsistency and complexity of the structure among different models. Across the Wrangell volcanoes, we see a high velocity feature right below the volcanic region, outlined by the dashed area here. So again, the subduction geometry is a very 3D feature. We wanted to check the most reliable features among different models. We computed the vote map from 6 models from 4 publications. We computed the positive values and the counts of positive values for the top 75% and normalized the count by the maximum number of models that cover that grade. So I want to emphasize here is that the vote map highlights features shared by multiple models, but they're not directly showing velocity values. Next slide, I'm going to show you an animation slicing through the vote map, 3D vote map. And there are a few elements within this within the model. One is the element, this is the purple color means high vote count, and green color means low vote count. And that means purple means you have multiple models observe the same feature. And this is the 410 kilometer steps. Below that is the mental transition zone. At the shallow part, we have the Delali fault here. And on the right is the location of the slice going from northeast to southwest. And this is the Southern Alaska coast. And you have a arrow pointing to north here, but we're looking toward the west and southwest. So there are a lot of features in this animation. So hopefully you have seen the decrease of complexity from Central Alaska or South Central Alaska to or Southwestern Alaska. And there are also very interesting deep slab signatures here. I want to highlight a few things. This is the cross-section or slice across the Yakta plate, Yakta slab, right along the plate motion direction. We observe 2 high velocity fissures, one below the Wrangell volcanoes and the other one below South Central Alaska. Moving further to the west, we see a large volume of high velocity signature here. Even further west and southwest, we see a high velocity feature, which is likely associated with the Alaska slab. So in summary, we have comparing and studied multiple models. From the clustering analysis, we have found that we are able to see the control of tectonic terrains on velocity structures, mostly in the crust. The Earthscope data has also enabled the image of deep structure below the slab. We are able to see very complicated and very 3-dimensional subduction geometry associated with the Yakta slab and the Pacific slab. So thank you for your time, and please contact me or any of us for any questions or comments you may have. Thank you.